Start video, share screen. But we don't actually start till 1:30, right? Do you want to hear Nina's snake story? I'll get time. So this is how much I don't like snakes. So I was at the house I'm living at now. This is our second uninvited snake guest. And I opened my front door and it was a small snake. The one I saw today was not a small snake, but the one I saw then was small. And oh, I need to do the eye clicker. I need to do this. And I opened the door and there it was in the middle of my front entryway, right? So me being who I am, I scream, right? Because that's, you know, that's what you're supposed to do. And the snake looks at me and then slithers up into the siding of my house. Oh no, not having it, right? I'm not gonna be able to sleep tonight. So I have nothing to kill a snake to get it. I have nothing. So I go in my garage, look for stuff, right? So I find a can of flying wasp spray. I find a hammer and I find a cutting pliers. So there I'm going, I go to my front door. Now this is all on a recording now, which is terrible. But so I crouch down because I have a glass door, you know, so I'm crouched down and I'm looking through the window and I'm waiting, right? And I tell myself, now you have to wait until the snake gets halfway, because if you don't wait, he'll go back into the siding and you will not sleep tonight, right? So pretty soon his little head sticks out. He starts slithering across and I'm like, gotta wait, right? So as soon as he gets a little more than halfway across, I throw open the door. I hit him with the spray, right? So now he's mad. And he starts twisting and curling and he goes into my rock bed with my flowers and plants and stuff, you know, in the front. And so I grab the hammer and oh yeah, it's this scene in front of my house, right? And so when he's finally kind of like stunned enough to be still, I get the cutting pliers and I'm cutting his head off, and you know, and so like the end of it, I'm standing in my front yard, I'm holding these tools and I'm going, you know, like I'm totally wiped out. And I hear the best part, this is the best part of the whole story. I hear from across the street, "You got something good?" Like, no, someone saw the whole thing. And it was a garter snake. I can't do it. I just can't do it. There's your fun story at Dr. B's expense today. Okay, you should be doing your seating chart. I'm going to minimize this. Oops, I don't know what I just clicked. It's too many things all in one place. Okay, so make sure you put your name on the seating chart so I know that you are here. You've heard my terrible snake story. It was terrible. But the snake today was worse. The snake today was big and it was black.
It's not your house?
No. So I when I saw it, I screamed, I threw a book at it, I ran inside. and brought my dog inside, you know, all this kind of stuff. And so I got some of that sprinkle stuff that's snake repellent, you know. And but like I didn't see it. I was sprinkling it and I didn't see it. And so I looked, I opened my hose, you know, like I have a hose on a crank thing, you know, but it doesn't have a bottom. And he was in there, he was curled up and he was in there. So I went and got an empty tote. And so I pulled the hose thing towards me and then put the tote on top of it. And then put a weighted umbrella stand on top of the tote. I was like, I'm not going to try and kill it because no, that's going to end poorly for me. So then I called my pest guy and I sent him a picture that I had taken of the snake. And so you can see the eye in the picture and you can see the eye is circular So you knew it was non-venomous versus vertical and being venomous. So he was like, I'll be there in 10. You're my hero. Yeah, it was sad, but that's how I feel about snakes. So I'm actually proud of myself that I didn't kill this one. I did not kill it. I wanted to, but I was not brave enough. I was so not, I really thought it was a water moccasin. I mean, like, I watched a little video that like compares a water snake and a water moccasin, you know, and I'm trying to figure it out. And of course I can't because I'm too freaked out. All right, so please check in on attendance and please check in on iClicker. So you have to put your name and you have to say, yes, I'm in the classroom, or no, I'm at home. And if you're on Zoom, you just put your name down here. Okay. So it's an eventful day. I feel like my blood pressure was way too high today. Okay, we got 2 more minutes. Questions, anybody? Everybody good? Yes, ma'am. I can't from here, but if you're still not, if you're still curious, send me an email, and like when class is over, I can go and pull it up. I can do roster. Okay, I can do this. Anybody else? But it keeps, every time somebody clicks in, it keeps pulling it back up. But yeah. Okay. So we got 1 more minute. Okay, and y'all are watching your videos, right? Yes. The what? On the videos? Well, and it's complicated, and we're going to do some more practice with the nuclear equations. Yeah, we're going to do a bunch today. So when you get to it, ask. All right, it's time. Okay, I'm going to preface this joke saying you have to picture not me doing this joke, but you have to picture my 9-year-old son doing this joke, okay? Y'all got that? All right, so knock, knock. T-Rex. What? There's a T-Rex at your door and you want to know his name? Y'all, that is his favorite joke right now. Do you want to know how many times I've heard it in the last 24 hours? Way too many, but I still have to continue to say who's there. So picture my 9-year-old doing that one. He loves that. All right, so before we start, I do want to say one more thing. I'm going to ask y'all for something. Today, I do not want to stop lecture to say, please put your mask over your mouth and your nose. I don't want to have to stop ever again for the rest of the semester. Because if you can't keep your mask over your nose and your mouth, I will ask you to leave. It's serious, okay? Now, most of y'all in here are going to be looking to be nurses, right? Yes, mostly. Okay, y'all are going to be the pillars of the medical community. You're going to hold up the medical community. So you have to lead as examples for everybody else, because everybody's looking at the nursing department as, what do we do? How do we do this right now, right? So y'all have to start being leaders. And I know that you can do it. And I know that it's possible. So mouth, noses, and mouths, okay? And we're good. I mean, if you take a drink of a bottle of water, whatever, that's fine, but then put your mask back, okay? Cool? All right, so let's do some chemistry. All right, we're gonna do iClicker first. Oh, so what do you normally take out when you sit down in class? You gotta be ready for iClicker. And if there's iClicker, sometimes you might need your calculator, right? So you should absolutely have a calculator out. What else should you have out? My best friend. Now, somebody asked me, and if one person asked me, that means that multiple people asked me. They asked me, where's my best friend on Moodle? Like, I need to know where my best friend is. You keep talking about my best friend. Where is my best friend? So go and find each exam. Immediately above each exam, these are the resources available on exam 1. I renamed it today as your best friend. Now, your best friend's going to change, right? Best friends change over time, don't they? Good best friends, they grow with you. So guess what your best friend is going to do? Your best friend is going to grow with you. So every time we have an exam, you're going to have your exam. Then here's your best friend who has grown with you. And I have to go ahead and rename them all. I'll go ahead and rename them all. But we'll learn more stuff and you'll get more stuff in your best friend. Okay, so our best friend grows with us over time. So when I give you your exam, I'm going to make a best friend copy for everybody and staple it to your exam. So you will get a packet that will be your exam, your best friend, and your answer sheet, and you'll just bring a pencil and a calculator. Okay, so when is our next exam? Next Thursday. So in 1 week, we have an exam. I know it's fast, but the perk is that it's only chapter 1 and chapter 2. It's not a lot of material. So make sure you're keeping up with the homework, you're keeping up with the lecture, videos. This class is all about keeping up and not getting behind. Absolutely. That is my #1 piece of advice. Do not get behind. And if you start struggling, please don't wait until Wednesday night to send me an email. I can't help you Wednesday night, but I can help you now. You know, make an appointment with me, go to tutoring, send me an email, right? Something. Okay, good. All right. Okay, so I'm gonna assume everybody's done that. We've done that. So much going on today. Oh, I'm clicking the wrong thing. No wonder. All right, iClicker questions. Y'all ready? View full screen. Okay, here we go. How many electrons, and remember this is by yourself. Let me end that poll. Oh, no, you're not in class. Here, okay. How many electrons are present in a neutral atom of potassium? So 1 minute, answer it on your own. I'll put my chat up in case people have questions on Zoom. One minute. Oh, I forgot to check how many responses we had on the first one. Then I know how many people are here. Anybody remember? You look at the number. Okay. All right, 10 seconds. Okay, so it looks like we have 45 today. All right, so now I'm going to run the same thing, but now you can talk. So go ahead, talk to anybody and everybody. I'll give you 30 seconds on this one. Remember, you got to check in again. So 10 seconds. Click in again. Don't forget to do that. You're like answering the same question twice. All right. So what did we say? How many electrons are present? Oh, 100%. Yay. Okay, so we went up. Don't you love this? Don't you love this system? So how did you do that? Potassium, did you go look for P? No, it's tricky, right? What'd you look for? K. But if you're unsure, what could you do? Use your best friend, right? And on the back of the periodic table, there's the list of the element names, and then you could look for the symbol. Okay, so K. So how many electrons are present? How do I know how many electrons are present? Right? If I look at the periodic table and I look at potassium, what on the periodic table, what's there? I have two numbers. I have a blue number and I have a red number, right? What's the blue number? What number numerically? 19. And what number do I have at the bottom? Yeah. Okay. So what is this 19 telling me? Number of protons. But that's not what I wanted to know. The question didn't ask me protons. What did it ask me? Electrons, right? But what did I know in this question? I was very specific about this, right? It was a neutral atom. But if I just say atom, it's also neutral, right? So in a neutral atom, number of protons is equal to number of electrons. Okay. All right. Let's do the next one. I graded that, right? Yes. All right. There we go. So I'll give you 1 minute. Atomic number is what? Remember, this one's by yourself. Ten seconds. Don't leave it blank. Don't ever leave anything for me blank. It breaks my heart. All right. I'm going to give you 30 seconds to talk to your neighbors. Same question. Talk to your neighbors, 30 seconds. Okay, don't forget to click back in again. Don't forget to click back in again, 10 seconds. I said that about 5 seconds late, so I'll give you all of 35 seconds. So 5 seconds, go ahead and click in. We had 45, didn't we? Click in, please, please, please. Please. All right. So what did we say? Okay, A or B, number of protons and neutrons, or just number of protons? It's number of protons. So we went from 86% to 95. That's awesome. That's awesome. Okay, so when I come back here to the answer that I did over here, right? This number of protons, this is the atomic number, right? So on the periodic table, when you look at that square, the whole number, this must be a whole number. It's a whole number because it's a counting number. I'm counting the number of protons present. Is this one down here a counting number? Why not? Got a decimal place. That's freaky, right? That's weird. We'll talk about what that is today. But that top number on the periodic table, that is your whole number, and that's your atomic number. Okay, so it is equal to the number of protons in each atom of our element. Ready for one more? You got this, right? I forget that I put slides that have the answers. Okay, so 1 minute. What do protons have? Tell me about protons. One minute. I feel like I need the Alex Trebek music or, you know, the Jeopardy. I need that. 10 seconds. It might be more stressful for y'all though. I'm not trying to stress you out. Okay, at 1 minute, I'm shutting it down. Okay, now turn, talk to your neighbors. I'll give you 30 seconds. Don't lower your mask to talk. Keep your mask over your mouth and face and nose. Okay, 30 seconds means you got 10 more seconds. So don't forget to click in your second answer. Click in your second answer. Okay, come on, y'all. There was more than 43. It was like 45. Y'all gotta click in again. It's gonna break my heart. Like one more. Come on, y'all. All right, so protons. What are protons? Right. So we have a mass of about AMU and a charge of +1. Good. Very good. Okay. Let's look at all of our answer choices. If we say that this is a proton, what's the question? Oh, sorry. Sorry. Okay, let's look at A. What does this answer choice describe? A mass of about 1 AMU and no charge. What was that? A neutron. That's a neutron. A negligible mass and a -1 charge. A negligible mass and no charge. A mass of about 1 AMU and a -1 charge. We only have 3, proton, neutron, electron, right? So only 3 of the answer choices are going to be correct. Okay. All right. So we can put away our clickers. So how y'all feeling on the clicker things? It's working out? You got it in the zone? Okay, so we were on the second page. Okay. I think we did we do 2.12? Did we do that one? Yes. Okay. So we're on 2.14. So this is the one I was telling you that you have to be careful about when you enter it in online. Let's do one and I'll show you that. So write the symbol notation for atoms. What is in general the symbol notation? Like if I just wanted to generally write it and X is my element, what number goes at the top? Now be careful because this is one thing and then this is something else, right? Okay, oh, trust me, I got it wrong in the last class because I was like still freaked out about the snake and I just, oh my gosh. So on the period, this is the periodic table. On the periodic table, this is the atomic number. That is true. Is it the same number at the top on the symbol? No. What's the number at the top? This is the mass number. How is the mass number different from the atomic number? Mass number is the number of things that have mass in the atom. So what things have mass? Protons plus neutrons. Okay, now at the bottom, what is that? This is our atomic number. And our atomic number is just what? Protons. So see how the atomic number was on the top in the periodic table, but when you write the symbol, it's now at the bottom. So is this number up here the same thing as this number? No, what's the number down here? What is this called? This is the average, and I'm going to actually even add something to it. It's the average weighted, and I'll tell you what that means later. The average weighted atomic mass, and the units are AMU, atomic mass units, right? Anywhere do you see the number of neutrons? No, but the mass number typically is a big number, right? because it's protons and it's neutrons. The number on the bottom is going to be smaller because it's only protons. So if I did this as a math equation and I subtracted the two, what would my answer be? Get a number. What's that number? What is that? I'm having quite a day. What is this number? It's my number of neutrons. So remember that when you set this up, you should be able to do a subtraction problem and you should get number of neutrons. That's a good way to remember it. It's like a math problem that's already set up for you. Okay. All right. I digressed. All right. Write the symbolic notation for atoms with 3 protons and 4 neutrons. So how do I know what symbol? I look at protons or I look at neutrons? Protons will tell me what symbol. So I go look on the periodic table, what has 3 protons? Lithium. So that's my symbol. Does the 3 go on the top or the bottom? Does the 4 go on the top or the bottom? You add them together, and when you add them together, you get the top number. So what number goes on top? 7. Okay. B. 7 protons, 10 neutrons. What element? Nitrogen. What number goes on top? 17. What number goes on bottom? 7. Oh, y'all are good. I can't even trick you. That was good. Okay. C. 15 protons, 16 neutrons. What symbol? What symbol? P, right? Phosphorus and potassium. You got to know which one's which, right? Okay. So what goes on top? What goes on bottom? Okay. D, 46 protons, 60 neutrons. What's my symbol? P? PD. Okay. So what goes on top? What goes on bottom? Good. Okay. Oh, and the thing I wanted to tell you, I gotta scroll down again. The thing I wanted to tell you before I switch the slide, right? When you're typing this in on the homework system, right? What you have to do is you have to insert a superscript and you have to insert a subscript, but it must be stacked on the homework. So what you want is a little box where you can put a superscript and a little box where you can put a subscript, and they must line up one on top of the other, and then you put the element symbol. So if it ends up looking like this, you didn't stack them, and it's going to mark it wrong. You have to stack them. And there's a button for stacked superscripts. There's a button for it. Question?
No, I literally had a question. I tried that homework and it was wrong.
Why is it wrong? It's probably because it was this. Yeah. So be careful with that. Make sure you stack them. Okay. Because that's what I was saying at the end of class last time. Okay. So now we're going to go vice versa. We're going to take the symbol and we're going to turn it into the number of protons, number of neutrons, and number of electrons. And remember, if I have this one, right, what do I do to get my number of neutrons? This is my mass number, so this is neutrons and protons. This is my atomic number, that's just protons. So I subtract the two and I get 1 neutron, right? Okay, so there's my neutron. How many protons? 1 right here. And then if this is an atom, what must it be? It must be neutral. So I must have the same number of positives and negatives, right? So if I have 1 proton, that's positive. How many electrons that are negative do I have? 1. Okay. I'm gonna do this. All right. So this was A, B, C, and D. All right. So B, how many protons? 13. Because that's the lower number. So I would automatically go and fill in my electrons. So how many electrons? 13. Now I go in and subtract 27 minus 13 is, okay. Next one, sodium. How many protons? 11. How many electrons? How many neutrons? 12. Good. Bromine. How many protons? 35. How many electrons? How many neutrons? Okay. Not too bad, right? Easy peasy lemon squeezy, as my son says. One of his favorite little sayings. Okay. The next thing we're going to talk about, isotopes. So when you think about isotopes, I want you to think about a general atom. If I have an atom that, for example, has 6 protons in it, what is it? I have 6 protons, 6p plus. What am I? Carbon. Okay, what if I have that atom and I take away some electrons? What element am I? I'm still carbon. I'm now an ion of carbon, right? Okay, what if I add a proton? What am I? I have to move. I have to become nitrogen, right? So I can't take away and add protons and still be carbon. But what happens if I take away neutrons? I'm still the same element. I'm still carbon, but now I'm an isotope of carbon. So you can have more neutrons or you can have less neutrons, but you're still carbon. Okay, so you've heard about this carbon dating, radiocarbon dating, right? So we have an isotope of carbon that's carbon 12. What is that 12? Mass number. So in carbon 12, how many protons? 6 protons. How many neutrons? Okay. We also have carbon 13. How many protons? How many neutrons? Oh, and carbon dating is actually done with, whoa, carbon 14. How many protons? How many neutrons? Okay, so do you see how no matter what, we still had to keep the same number of protons. All we did was change our number of neutrons. Now, if I said, what's the mass of a carbon 12 atom? What would you tell me? What is the mass of a carbon 12 atom? 6 and 6 is 12, right? Should have a mass of 12 AMU. How about carbon 13? Should have a mass of about 13 AMU. Carbon 14 should have a mass of about 14 AMU. So what if I took the average of all of my isotopes? What would my mass be? My average mass? Go answer this one first, I promise. What would the average be? 13. The average would be 13. But Dr. B, I'm looking at the periodic table and the average atomic mass is not 13. What is it? 12.011. But I thought the atomic mass was the average of the isotopes. It's not a simple average. It's what kind of an average? A weighted average. What does that mean? You're never going to have to do this calculation, but I'm going to show you how it's done. You're never going to have to do this calculation, okay? When I do this, I'm going to do an average. How do I do an average? 12 plus 13 plus 14 divided by 3. This is an average, right? Now, I want to do a weighted average, right? So what I do is I take the numbers I want to get the average of, and I look at how abundant they are in nature. So I'm going to tell you carbon 12, 99% of all carbon on the planet Earth is carbon 12. 1% of all carbon-13. Oh, I'm sorry, 1% of all carbon on the earth is carbon-13. And then carbon-14, I'm just gonna write tiny. Because it's not even worth writing the number. So how do I take that into account when I make a weighted average? I need to take that percentage into account. So I convert that percent to a decimal. So what is that in decimal form? Then I'm going to add that to my carbon-13, and I'm going to put the percent. What's the percent in decimal form? All right, 14, I'm just going to put it, and I'm going to put tiny. Because it really doesn't even factor in, okay? And I'm going to divide that by 3. And when I do that, I get 12.011. So just looking at the atomic mass on the periodic table, I can make a prediction. What prediction could I make? The most common isotope of carbon is what? Carbon 12. Why? Because the average atomic mass is closest to that isotope, the most abundant isotope, its mass is closest to the average atomic mass of the element, right? That you have to be able to predict. Will you have to do this math? No. Do you have to understand it? Yes. Make sense? Okay, let's go answer some questions. Now that I've gone off on my tangent for a while, I do that. Okay, so let's do this. The mass of the isotope carbon-12 is exactly 12 AMU. The atomic mass for carbon, as seen on the periodic table, is 12.01 AMU. Explain that difference. So how would you explain that difference? We just talked about it. What do we say? Say again?
The one that's on the periodic table is a weighted average.
It's a weighted average, okay? So the atomic mass, right? The atomic mass is a weighted average. So what? So the atomic mass takes in to account the abundance of all isotopes, isotope masses. Think that way. Right? The more prevalent the isotope is, the greater the impact it will have on the atomic mass of the element. So I used to do this little lab. I called it Snackium. And we took a bag of like Chex Mix, right? And we said the bag of Chex Mix is an element. So everything inside of that is an isotope of the element Snackium. So the heavier things inside of the mixture really give the average atomic mass of the element, right? Because there are more of them, right? Whatever you have the most of, that's going to contribute to the average of the most. So you might have one or two things that are really heavy, right? But is that going to contribute to the average mass? You know, like those big wafery things, those are kind of heavy, but there are way more of the little light Chex Mixy sort of looking things, right? So they contributed to the mass more. So it's whatever's more prevalent is going to contribute to that average mass the most. Okay. How are atomic mass and mass number similar? How are they different? I'm going to start with how they're different, kind of easier. So tell me about atomic mass. You just told me this. the average, right, weighted mass of all isotopes. Now tell me about mass number. It's actually not a mass. Like, we want to say mass number is a mass, but it's not really a mass. Really, what are we doing? We're counting. So whenever you see number, you should be counting, right? So this is a count of the number of what? Protons and neutrons of what? I would say an atom, or I would say an isotope of an atom, right? Whereas our atomic mass is the average weighted mass of all isotopes of what? An element. What's the difference? Right? An element includes all isotopes. One isotope can only be one isotope, or an atom can only be one isotope, but an element is all the isotopes. Okay, how are they similar? I don't know why I did a line there, but how are they similar? Both depend on what? The number of protons and neutrons. That's right. But in different ways. That always makes it kind of complicated. Right? Okay. All right, now, I don't know why I didn't do this yet. There are 3 naturally occurring isotopes of magnesium: magnesium 24, magnesium 25, and magnesium 26. We want to know how many neutrons are present in each isotope, and we want to write the complete symbolic notation for each isotope. So let's do that. But magnesium, what's my symbol for magnesium? Mg, and magnesium, no matter what isotope it is, must have what? Magnesium must have 12 protons. Supposed to be a plus sign. So if I'm going to write, let's write our symbolic notation first. It's going to make it easy. So magnesium 24, how do I do that? Does the 24 go on the symbol? I'm doing this one, magnesium 24. It goes at the top, 24, the big number goes at the top. What goes at the bottom? 12. Why did I want to write the symbol first? Now I've got my subtraction problem all done for me, right? So if I find the difference, I'm going to find the number of neutrons in each isotope. So how many neutrons are present in magnesium 24? 12. So I'm going to say 12 neutrons for magnesium 24. Okay, so let's do this for magnesium 25. And don't leave this. If you're asked for one, don't leave that. Erase it. All right, magnesium 25. What goes on top? 25. What goes on bottom? 12. Okay, how many neutrons? 13 neutrons. Okay, magnesium 26. How do I write that? Mg 26 at the top. What goes at the bottom? 12. So how many neutrons? 14. Because we went 24, 25, 26. So our mass increased by 1, but our number of protons never changed. So we just increased by 1 neutron every time. Based on the average atomic mass, what is the average atomic mass given on the periodic table? Look at magnesium. What do you get? 24.30. Which isotope of magnesium is the most abundant? This I may ask you on an exam. The one that is closest to the average atomic mass. Which one is closest? Magnesium 24. So you could answer this way, or you could answer this way. Either one is correct. We're saying the same thing. Okay. All right. Some of the naturally occurring isotopes of tin are tin 118, tin 119, tin 120, and tin 124. How many neutrons are present in each isotope? I'm going to skip that. I'll come back to it. Write the complete symbolic notation. So let's do tin 118. What's my symbol for tin? SN is 10. That's so weird. Okay, what goes on the top? 118. What goes on the bottom? 50. All right. 10 119. What goes on the top? 119. What goes on the bottom? Ooh, y'all on the ball. Okay, 10 120. What goes on the top? What goes on the bottom? Okay, 10 124. What goes on the top? What goes on the bottom? Okay, now write A. Now we're going to do A. How many neutrons are present in each isotope? How many neutrons are present in tin 118? So how'd you get that? All we did was subtract. Okay, 119, we went up by a mass of 1, but we stayed the same element. So how many? 69. Did I have to really do the math? No. Okay, 120, how many? 124, how many? 74, because we went up by 4. Okay. All right. So now comes the cool part. All right, so radiation. When we talk about radiation, there are some forms of radiation that are more dangerous than other forms of radiation. And that's because they are made of different particles, and those particles behave differently. And they can get through different materials and have all kinds of different applications. So I want you to take a quick look at your best friend. Do you find this table on your best friend? You're gonna be sad your best friend's letting you down today. Your best friend's letting you down today. So I'm telling you that you need to know this table. But if you only know the first 2 columns, you'll know the rest. And I'm going to teach you why, okay? So I'm like starring, circling, you need to know this. You need to know this. Every now and then I do this. You need to know this, okay? Telling you that on the front end. All right, let me get rid of all this stuff. So the types of ionizing radiation are alpha, beta, gamma, positron, and neutron. Now, these top ones, we're all going to kind of lump together because typically they are emitted. While a neutron can be emitted, a lot of times what we use this for, especially in medicine, is to create radioactive elements, right? How do we use radioactivity in medicine? For an example, we use it in radiation, giving a patient radiation who has cancer, right? So if I'm going to give someone radiation, I have to make a radioactive element. How do you make a radioactive element? What makes an element radioactive versus non-radioactive? It's really the ratio of protons and neutrons in the nucleus. There's a stable sweet spot. And if you add too many neutrons or you take too many neutrons away, that atom gets super unstable and really unhappy, and it needs to get back to that stable point. And so what it's going to do is it's going to emit things in order to get back to that stable point. That's emission. But what if I have this stable atom and I want to make it radioactive? What could I do? I want to change the number of neutrons. Could I add some neutrons? Sure. Neutrons. I can add some neutrons and that'll change my relationship, right? And it can make it unstable. So a lot of times neutrons we use in bombardment as well as emission. So bombarding and emission. So when we look at these, alpha radiation, you could use the little symbol A. I don't want you to use that because it doesn't tell you any information. Look at the other way that we can represent alpha radiation. What do you see? Helium, right? Why do we call it helium? Look on the periodic table, look at helium. How many protons are in helium? 2. Now look at an alpha particle. How many protons are in an alpha particle? 2. Okay, in a stable helium nucleus, we have how many neutrons? 2. How many neutrons are in an alpha particle? 4 minus 2 is 2. So we have 2 protons and we have 2 neutrons in an alpha particle. So if you learn that the alpha particle symbol is a helium nucleus with 2 protons and 2 neutrons, you have all the information you need, right? Because if you have that, what's your charge? If I told you it's just the nucleus, it's just protons and neutrons, what am I missing? Electrons. So is it going to be neutral? No, it's not going to be neutral. It's going to have a charge of +2 because this is a helium nucleus. So it has no electrons. That's what an alpha particle really is. So what should the mass number of that alpha particle be? 4, because we have 2 protons, 2 neutrons, mass of 4. Okay. All right, a beta particle. In a beta particle, what we are doing is we are actually emitting a high energy electron. But you're not emitting an electron that was already present. What you actually have is a proton that is being converted into a neutron and an electron, and then the electron is ejected. So if I just eject an electron, does my mass change very much? No, but I just told you I took a proton and I turned it into a neutron and an electron. Am I still the same element? No. So what you're going to see in beta radiation is that your elements change because they change the number of protons. So if I took a proton and I converted it into a neutron, what should happen to my atomic number? Should it go up 1 or down 1? Should go down 1. So look what I have. A -1. That's why it's negative. And that helps me to remember, oh, and I'm also releasing a high energy electron. So that's where the -1 comes from, right? So should it have a mass? No, 0, right? Okay, gamma radiation. Gamma radiation is just rays. It's just waves of radiation. There are no subatomic particles. So you're not going to have a charge. You're not going to have a mass, right? This is similar to X-rays, but way higher energy. So it's way more dangerous to be around gamma radiation than it is to be around X-rays, right? We get X-rays all the time, but I'm very concerned for you if you're exposed to gamma radiation, okay? All right, positron. And look, we're not using the symbol B, right? For that one, I forgot to X that out. We're not using that. Well, I mean, it's there, we're using it, but don't use it. Okay, a positron. A positron, we are emitting a positively charged particle, right? So look at your charge. What's your charge here? A +1, a +1. So in a positron, what's actually going to happen is that you're going to have a neutron converted to a proton. So it's going to be a positive charge. So what's going to happen here? Look at is your mass going to change? No. What's going to happen to the number of protons in the atom? is actually going to decrease. It's actually going to decrease because you're releasing one proton. Here, this positron, I am releasing one proton. And that's the release. The symbol is what's released, right? So your element is going to change because your number of protons is going to change. And I'll show you this when we do equations. The last ones are neutron. So do our number of protons change if we emit a neutron? No, it's a 0, right? But what happens to our mass? Mass goes up. But we're not releasing anything that's charged. So our charge, it's uncharged, and it has a mass of 1. Okay, so if you know this part, oops, well, you know what I mean, as I run through everything. If you know these 2 columns, you're good. Okay, and notice the beta and the positron. What's different between these 2? Negative and a positive. A beta is emitting a high energy electron, so that's how I remember it's negative. A positive, if there's nothing there, it's really positive, right? So it's a positron, it's positive. Okay, that's how I kind of remember it. All right, what's the charge on a beta particle? I don't want you to look. What symbol do we write for a beta particle? E0, -1. So what's the charge? -1. Okay, an alpha particle. What's the symbol for an alpha particle? Remember, a helium nucleus, 4 and 2. Oh, I have these 2 positive things down here. What's my charge? +2. Okay, a positron looks just like a beta particle, except it's positive. So I'm not going to put the charge, but it really is a +1. So that's a +1. So if you know the symbols, you can answer all the questions about them. Okay, and I think I didn't erase this from last time. I don't know how that works, but okay. So what form of ionizing radiation is most similar to X-ray radiation? We said this, gamma. Why? There's no subatomic particle. We're not saying it's an electron. We're not saying it's a proton. We're not saying it's a neutron. It's a ray, right? So it's no subatomic particle. How is it different? It's more what? More dangerous, more high energy. High energy. Okay. So how often do you get exposed to radiation? Like all the time, like all the time. Is radiation good for you or bad for you? It's bad for you. So for example, if I would go out in the sun for, I don't know, 20 minutes on a nice, bright, sunny day, you know what would happen to me? I would be sunburned. I do not tan, I turn crawfish red, and I turn back to white. That's just me. So why do I get sunburned? So there is UV radiation that my cells absorb. What is so dangerous about that? What does that UV radiation do to my cells? No, it doesn't. It does not kill them. It changes the DNA. It actually mutates my DNA. But my cell's still there. But the cell has mechanisms that recognize that DNA damage. And it actually puts little flags on the outside of the cell that tell the immune system, hey, I am messed up. I do not need to replicate. You need to come and kill me. And the immune system will go and kill those cells, right? So that's why you get red, because your immune system has gone and taken care of those cells. Really, really. Okay. But if I have a patient who comes in who has cancer, Would giving them radiation be harmful to them? Yes, yes, it would be. Radiation, pure and simple, is bad and dangerous, right? Okay, so why in the world do we treat cancer patients with radiation and chemotherapy for that matter, right? What's radiation is what we just talked about. Chemotherapy is a drug that's toxic. So if the cell takes in the toxin, the cell's going to die. Okay, that's the difference, but they're both harmful. So is the radiation not harmful for some cells and other cells? No, it's still just as harmful for both types of cells. So what's the difference between cancer cells and healthy cells? They grow, they grow, they grow, they grow, they grow. All they think about is eat, grow, eat, grow, eat, grow, eat, grow, right? So they can go through many, many, many rounds of cellular replication and replicating their DNA. So if you bombard cancer cells with radiation, they are going to accumulate more mutations to the point where they won't even be able to replicate because their DNA is so damaged, and therefore they will die. But what's happening at the same time? You're killing good cells in the body. I don't care if you're doing chemo or radiation. You are killing cells. You are killing cancer cells. So cancer cells grow. Let me write this before I get too far ahead of myself. Cancer cells grow very rapidly. So they accumulate more mutations. So these die, but your regular cells die. But the point is that the cancer cells will die first. F-I-R-S-T, first. Cancer cells. Because they're highly replicated. They're highly replicative. So tell me, if you have a patient who comes in to get chemo or radiation, what symptoms do they have? Nausea, hair loss. Those are the two big ones. Let's talk about those. Why?
Because the stomach lining cells replicate, but also.
So when you think about your stomach is making hydrochloric acid all the time, right? So at some rate, you really are eating yourself because you're killing the lining cells of your stomach, but your lining cells make mucus, which protects to some degree, but they still get damaged. So they replicate very quickly because they have to be replaced. So in a person who's getting chemo, radiation, that kind of stuff, those cells die because they're dividing rapidly, because that's the target for chemo and radiation, is rapidly dividing cells. Same thing with hair follicle cells. They grow at a very rapid rate. So that's why they fall out. It's just because it's targeting rapidly dividing cells. Chemo and radiation do not target cancer cells. They target rapidly dividing cells in the hopes that the cancer cells will die before you do. That's the way it works. So you have to be very, very careful in how much radiation you give someone, how much chemotherapy you give someone, because usually you're doing it in combination, right? I mean, this is really, really hard on the body. I think the new wave of medicine is going to be specialized for the person because of their genetics and their receptors on the outside of the cells, but that's a whole big another conversation. but that's why we do chemo and radiation, right? Any questions about that? We went kind of off target, but that was interesting, right? Okay. I think I did this wrong because I think this one's answering this one, but let's answer 28 first together, and then we'll talk about 27. So how many simultaneous chest x-rays would a person have to endure to have an exposure of 20,000 milliriems? So 20,000 milliriems is the first point in which we can medically say you will have a physiological change due to that radiation. And the first thing that we see is a decrease in white blood cells, because we know those replicate relatively quickly, right? So this is a way for us to say, oh, here's a marker, you're getting a little bit of radiation here, right? So how many simultaneous checked X-rays would you have to get if 5 millirims of radiation is the average X-ray? So I know that I have 20,000 millirims. I want to know how many times can I get 5 millirims before I get to 20,000, right? So 5 times X gives me 20,000. Divide by 5, how many X-rays is that? 4,000 X-rays. So is it okay to go and get an X-ray on your teeth once a year? And your foot when you break your foot? And it's fine, you'll be fine, right? Who has to worry about it? X-ray technicians. What do they do? What precautions do they take? Okay, so they have a badge, they wear an apron, and sometimes they even leave the room, right? They're like, peace out, I'm going over there, right? Well, it's really important because they don't need to be accumulating excess radiation. That badge that they wear, so the apron that they wear is lead lined, and so most radiation won't pass through that. So that's why they wear the apron, right? But the badge that they wear is a badge that basically will follow you for your entire life. So every so often you'll get a new badge, but that badge is linked to your social security number. So you actually get monitored for your total lifetime exposure. And that's really, really important. I did some research with radiation when I was in New Orleans. I worked at the Louisiana Cancer Research Consortium, and I did experiments with radiation. And so I had a badge, and it's linked to my social security number. So if I decide I'm here at Nichols and I want to do research that has radiation, I'll have to contact the safety department and they'll issue me a new badge, but that new badge is still linked to my old information, and then it adds up, right? And I mean, it's serious. If you work with radiation, you have to be insanely careful, insanely careful. All right, so the question is one X-ray harmful? One X-ray is not harmful, but an accumulation of X-rays is extremely dangerous and can lead to things like cancer, right? So you need to monitor that. All right, let's see. So then a routine dental exam often includes 4 bite wing X-rays exposing a patient to a total of 5 millirims of radiation. Would this cause radiation sickness? No, because what do you have to get to start having a biological effect? 20,000 millirims, that's a lot, right? So you're not going to get sick. Go get your X-rays, it's not a big deal. But if you're an X-ray technician or someone that handles radiation on a regular basis, you do have to be super careful. All right, so the next thing that we're going to do is we are going to do some balancing chemical equations, but these are nuclear equations. So in the nucleus, what things do we worry about? Protons and neutrons. And we can do that by just looking at 2 numbers. What 2 numbers? We call this the mass number. And what do we call this one? The atomic number. Okay, so whenever we have radiation occurring, we have some kind of a reactant. I'm going to draw that reactant as a square. Okay, I'm going to tell you that this square is going to degrade or decay, right, into 2 triangles. How should I write this equation of a square degrading into 2 triangles using my standard arrow and stuff? Should I put plus a triangle? No. So I have to listen to the words that are inside the problem. If that square is going to degrade, right, I'm going to cut it like that, right? It's going to break down into, okay, it's not perfect triangles, but you know what I mean, right? Into 2 triangles. So make sure that you listen to the problem to know where to put it. A lot of times when y'all go wrong on these problems, that's where you go wrong. You start wanting to add one of the triangles to the square, but be careful on that. Okay, all right. And I think I did that one. Okay, where am I picking up? Here. Oh yeah, and I made this mistake. I made sure to highlight this. I'm sorry, I was doing this in the recording. I did A, B, and C for 2.29, and then somehow I picked up D for 2.29, for 2.30. So I don't know how I did that, but I did. I'm so sorry. I'm so sorry. So what we're going to do is we're going to do A, B, and C for 2.30, and then we're going to pick up this one. Okay, so I'm sorry. I got that mixed up for you. All right, so let's make our nuclear equation. We have thorium-232. How do I write that in symbol notation? Thorium is what? Get your best friend, TH. TH, thorium is TH. What goes on top? 232. So find thorium on the periodic table. And how many protons do we have? 90, so that goes on the bottom. Okay, thorium undergoing alpha decay. Where should I put my symbol for alpha? So should I do plus? No, I need an arrow because thorium is undergoing decay. What kind of decay is it? It is alpha decay. So what's my symbol for alpha? And 4 at the top and 2 at the bottom. Plus, you got to look at that. Thorium has 90 protons, right? And I only released 2 of them. So there's going to be other stuff left over, right? You don't decay a square into 1 triangle. You decay a square into 2 triangles, right? So same kind of concept. So when I think about this, the numbers on top, just like in a balanced chemical equation, are like the coefficients. Pretend that there's an equal sign. So 232 is equal to 4 plus what? $228, because 228 plus 4 is 232. Yeah? Okay, so let's do the same thing with the bottom numbers. 90 is equal to 2 plus what? 88. What symbol should I put? Ra, radium. Yeah, you could do this. Okay, B, strontium 92. What's my symbol for strontium? SR. What goes at the top? What goes at the bottom? Strontium is 38. I thought I heard 88, 38. Okay, it's undergoing beta decay. What's your symbol for beta? Remember, beta is an electron, a high energy electron. Okay, but that -1 is not really saying it's an electron. What is that -1 really saying? It's talking about the protons, right? Okay, so plus we're gonna have something formed. So we gotta make our reds equal and we gotta make our blues equal. So let's do the reds first. 92 is equal to 0 plus what? 92. Let me do that in red and black, 92. Okay, now be careful with this. 38 is equal to -1 plus what number? 39, because you really have to do this plus 1, right? So that gives you 39 is equal to X, right? So be careful about that. So this one is 39. So what element? Yttrium. Yeah, weird one. Okay, so just be careful about those negative signs. All right, let's see. And then we need to go pick up, no, we still got to do C. Okay, C, nitrogen 13. So that's nitrogen. What goes on top? What goes on bottom? 7. Undergoes positron emission. So I'm going to emit a positron. Remember, a beta and a positron are really similar, except what? It's positive. Okay, plus something. So I want to make my reds and I want to make my blues equal. What should go in the red? 13. Okay, what should go in the blue? 8 or 6? 6 plus 1 is 7. So what element? Yeah. All right, last one on D. I'm gonna pick this D up. So weird, I know, I'm sorry. Okay, so carbon 11, what do I put at the bottom? 6. Undergoing positron emission. So positron is just like what we did before. We got to make our reds equal. We got to make our blues equal. So what goes on the red? 11. What goes on the blue? 5 plus 1 is 6. So what element? Boron. Yeah. All right. Last one on this page. Write a balanced nuclear equation for the production of iodine 131 used in the treatment of some cancers from the beta decay of tellurium 131. They gave you all the pieces. They gave you everything. What do they want you to do here? Make sure you know where it goes. Oh, tricky, right? Okay. So tell me about this iodine 131. What is that? A reactant or a product? It's a product because it's the production of. So that's a product. How about tellurium 131? That's a reactant because that is what is doing the decay. Now tell me about beta. Reactant or product? Product. It's the beta decay of tellurium. So tellurium is undergoing beta decay. So how should I write this? What do I start with? Tellurium, which is the abbreviation. TE, what goes on top? 131, what goes on bottom? 52. Now what? Arrow yields. And it doesn't matter which one you put first. We've been putting the radiation particles. So let's do that. So what's beta? Okay. Plus what? Iodine. What goes on top? What goes on bottom? 53. Does my math work out? Like check to make sure your reds, do the reds equal? Yes. Do the blues equal? Yes. I gave you all the information. It's just about reading the problem and knowing where it goes. Okay. All right. And I think we're going to stop right there. We finished it. We did get caught up. We got caught up. We did great. Y'all did awesome. So we will start with section 2.6 next time. And then what happens the next time I see you? Exam 1. You got this. Okay, anybody? Oh, I got rid of my chat. Oh, I'm so sorry. Anybody on chat need anything? Oops. Yeah, let me, hold on. If anybody needs anything, go ahead and put it in the chat. Otherwise, I'm going to go ahead and end the Zoom. Okay. So if y'all need anything, just send me an email.